So hi everyone, I'm Sachi. I'm a grad student in electrical engineering, and I'm going to be going over RF genesis, zero-shot generalization of millimeter wave sensing through simulation-based data synthesis and generative diffusion models. It's a huge mouthful, but I'll try to make it more bite-sized. For the presentation outline, I'm going to be going over the introduction, then related work and motivation, methods, implementation and integration, setup, system evaluation, case studies, and then a conclusion. So for the introduction, the paper really sets the stage for the development and application of RF genesis, which we're going to call RF Gen from now on. And that's a new method designed to enhance the generalization capabilities of millimeter wave sensing systems. And recently, there's been a rapid advancement and integration of wireless sensing technologies into multiple facets of human life. And in the image on the right, we can see, for example, a wireless sensing used in autonomous driving. And among these technologies, millimeter wave sensing is spotlighted for its potential attributed to its high angular and range resolution. And this resolution allows millimeter wave sensing to offer vision-like capabilities like tracking gestures and movements. Generalization is the model's ability to adapt properly to new and previously unseen data. And this poses a challenge, especially for millimeter wave sensing, because they have a high sensitivity to environmental changes and user variation. So unseen scenarios will lower the performance of those systems. And usually to make those more reliable, we'll use deep learning, but it's really hard to generalize well to new data because of the large and diverse data sets needed to be collected to train the models. Just collecting the vast and varied data sets to improve the generalization is impractical, and this is because there's a lot of cost with the specialized equipment and the specificity of data to radar configurations. And while simulators for synthesizing data have shown promise in fields like computer vision, they have not been widely adopted in RF sensing. And this is because of RF sensing data really needs detailed scene information like object geometry, material properties, motion, which are challenging to obtain and model. So RF Gen is proposed to address these limits. By using a cross-modal generative framework, RF Gen synthesizes and expands millimeter wave sensing data, bypassing the need for the extensive real-world data collection. And as seen on the right, RF Gen will use many methods that we're going to go over in order to do this. The system combines a custom ray tracing simulator, which models RF prop and interactions with objects and environments, with diffusion models that generate large-scale 3D scenes and their corresponding millimeter wave data. And before we go into the specific methods, let's get a little bit of context on what it's building upon. So satisfactory generalization is a challenge because of the RF signal propagation and interaction. Data augmentation and neural style transfer, as seen on the right, can also try to address this problem, but they fall short in representing accurately the complex multipath effects in wireless signals. There's also so much unexplored potential in this space. Generative diffusion models have shown promise in a lot of fields, but have not really been applied to the RF domain. And the same thing applies for the simulation-based cross-modal data synthesis. So what's the overall goal? RF Gen has the transformative potential to address the critical need for diverse sensing data. And the goal of the paper is to have RF Gen enable enhanced generalization across a wide range of applications without the constraints of data collection and model training. So one of the methods discussed are physical simulation models, and the synthetic data is used to train and enhance millimeter wave sensing systems, significantly improving their ability to generalize to new environments, objects, and movements not present in the initial training datasets. And the first physical simulation is a path tracer, which is essentially a sophisticated ray tracing algorithm designed specifically for RF Gen. And it simulates the emission, propagation, and interaction of electromagnetic waves within the 3D environment. Recognizing the computational intensity of ray tracing, RF Gen incorporates an adaptive sampling strategy, and this focuses computational resources on areas the scene will most likely contribute to the received signal, like edges and boundaries. And then you can kind of see that in the picture. And our understanding RF signal behavior when working with different materials is also important, and derived from Maxwell's equations of Fresnel coefficients allow for the prediction of the reflected and transmitted radiation. The materials are modeled in the simulator by assigning relative permittivity and permeability values, encompassing a range from non-conductors to conductors, and the equations on the left describe those properties. In the simulator, the Fresnel equations determine reflection and transmission rates at boundaries, influencing received signal strength. The ray tracing simulator using the Fresnel model manages reflection, transmission, and absorption. So that first equation has I as the incident direction vector and N is the normal vector. And that second equation has RP and RS as the reflection coefficients for parallel and perpendicular polarization. The signal generator component utilizes physical optics integral method, which is a simplification that allows for efficient computation of scattered fields over object surfaces. The simulation accounts for material-specific reflections and transmissions using the Fresnel equations, which consider the incident angle, polarization, and material permittivity and permeability. And the final step includes calculating the radar's received signal based on the path information generated by the path tracer. The use of generative diffusion models allows RFGen to create highly diverse and realistic datasets for millimeter wave sensing applications. This approach enables a synthesis of data that accurately mimics real-world conditions, improving the generalization capabilities of millimeter wave sensing systems. The first generative diffusion model is object diffusion. It uses prompts to generate objects and their movements within a scene. This component focuses on creating detailed mesh models and associated motions that are then used by the physical simulation models for further processing. So in the image in this slide, the object diffusion model takes the prompt that the person is running back and forth as an input and outputs the target object with the corresponding motion that can be directly used by the simulator. The second model is PUR and LoRa. PUR is the path-based intermediate representation, and it's a novel representation introduced by RFGen to facilitate the integration of diffusion models with physical simulations. It encodes the path of RF signals in an image-like format, like you can see in the middle, allowing generative models to understand and manipulate RF signal characteristics. RF path low-rank adaptation is an adaptation technique that modifies pre-trained diffusion models to work with PUR. And it allows RFGen to leverage the knowledge captured by these models in other domains, like image generation, and apply it to the synthesis of RF data. The last two models are environment and path diffusion, and I really like this figure because it really shows how everything works together. The environment diffusion is aimed at generating environmental features and conditions based on prompts. And you can see, for example, on the top left, living room prompt is used to generate that living room image. It helps in creating varied backgrounds and settings for the synthesized RF scenes, adding layers of complexity and realism to the generated data. Path diffusion enhances the results from the object and environment diffusion by refining the signal paths and interactions generated by the physical simulations. It focuses on correcting and improving the final synthesized RF data to ensure it accurately reflects realistic scenarios. Here we can kind of see how the physical simulation models and the generative diffusion models are integrated within the whole system. So starting very high level from the left, we have RF sensing prompts that feed the generative diffusion models along with the existing datasets, and the outputs from there feed into the physical simulation models, which provide the RF dataset for the RF sensing systems. RFGen's implementation is designed to be adaptable to different radar platforms, showcasing its versatility. And the paper specifically mentions configurations for some TI and Infineon platforms and how it can accommodate a range of radar specifications. For each radar setup, RFGen is carefully configured to simulate specific radar characteristics like output power, antenna placement, and gain patterns. And moving set sensing models, RFGen synthesizes data that is directly compatible with existing RF sensing models. And by generating ADC sample data, it allows for an integration with current millimeter wave sensing systems. And a base example is millimeter mesh on the right, and facilitates straightforward augmentation of training datasets without requiring modification to the sensing models. And finally, RFGen leverages pre-trained diffusion models as a foundational concept of its data synthesis process. These models are made to generate data within the PUR and LoRa method that I discussed before. So that's the path-based intermediate representation format, and it's going to be using the path low-rank adaptation method. The setup is pretty comprehensive, and it emphasizes comparing the synthetic data generated by RFGen with real-world data collected from radar hardware. So there's 10 participants with 5 male and 5 female, and it's evaluated in 10 different environments. And as shown in the figure, it includes both indoor and outdoor open space, different times of day and different weather conditions. And in terms of hardware, millimeter wave radar sensors along with RGBD cameras for both depth and color are used to capture ground truth data for both the physical environment and the subject's movements. The system was evaluated in multiple stages, and the first is being with the RF simulator. They compared the millimeter wave signals generated by RFGen simulator and those collected from real-world radar sensors. In the signal level evaluation, fundamental information like range, phase, and speed are focused on. And in these experiments, they use actual radar hardware to capture that ground truth and the point cloud while using an RGBD camera to get the 3D mesh, which is used as an input to the RF simulator. On the right, we can see the comparison of both the simulator outputs with the ground truth. And here the participants are walking back and forth. The simulator's raw time domain signal is converted into a spectrogram and dynamic range angle image. And these both resulted in having over 0.85 SSIM, which is structural similarity index, and over 30 for the PSNR, which is peak signal to noise ratio, which would suggest that there's a high degree of structural similarity between the two signals. On the point cloud level, the information that's focused on is the accuracy of the 3D scenes, including attributes like the shapes and sizes of objects. Point clouds measure points on external surfaces of objects, and the Hausdorff distance is the greatest of all Euclidean distances from a point in one point cloud to the closest point into another. The average distance of that was 0.37 meters, and since that is a minor fraction of the average human height, it's deemed satisfactory for this test. And because it's low, it shows that it's efficient in replicating signal features at the point cloud level. RFGen is shown to apply to different radar platforms, like I mentioned, including these two TI radars. And the evaluation highlights the ability to accurately simulate the distinct characteristics of each platform, as evidenced by the low Hausdorff distance measurements. The authors also discuss the approach to generating structured noise to simulate environmental multipath effects like reflections, diffraction, and scattering off surface objects. The authors compare RFGen's performance against other methods like additive white Gaussian noise and neural style transfer, which we mentioned earlier in the slides, which add random noise to the signal and adapt style of one signal to another, respectively. And when comparing recognition accuracy in environments that are part of the NST training set, RFGen performs comparably to NST, showing its capability to generate high fidelity and realistic data. And the baseline system that they use is millimeter mesh, which is a deep learning based system that constructs the dynamic 3D human mesh in real time. And that's the picture that I presented as the baseline example before. RFGen outperforms both of the methods in environments not covered by the training data. And this shows that RFGen is better than AGWN and NST in terms of generalization. The next evaluation examines how RF sensing prompts affect the quality of the generated data. And through iterative tests with varying prompt complexities, the study finds out that detailed prompts result in a higher quality synthesized data, which in turn improves the sensing system's performance. So as a micro benchmark, the authors chose the action of jumping. So you see this man jumping here. The table shows the different prompts that are increasingly precise, with P4 being the most complex, with both positive prompts that encourage favorable outcomes and negative prompts that encourage critical or unfavorable outcomes. And on the left, you can see the recognition accuracy. And as we go from P1 through P4, we find out that better crafted prompts yield to a higher data quality. Moving on to system evaluation. The next evaluation is about RFGen's computational demands, which covers both simulation models and generative diffusion models. The physical simulation models have a common runtime complexity, and that's O log n, but the generative diffusion models are way more computationally reliant in that the diffusion models need more resources. So if you look at that bottom example, for RFGen to create 1,000 unique action data set for the TI AWR 1843 radar, it takes 5 hours a day on the RTX 3070, with samples taking 20 seconds to 2 minutes each. Now moving on to case studies, there are different evaluation metrics to assess the performance. Here are some of them. They're going to be on the slides in the future, so you don't have to memorize them. But V evaluates the average distance between the vertices of the actual 3D meshes and those constructed with the millimeter wave signals. S measures the error in localizing joints in the reconstructed human pose compared to the actual one. Q quantifies the error in estimating the rotation of joints in the reconstructed pose. T assesses the difference between the actual and estimated location of the entire mesh in 3D space, and G assesses the model's accuracy in predicting the gender of subjects based on the 3D mesh. And for all these a lower number is better, except for G. And the first case study to show The first case study will show how RF-Gen enhanced millimeter wave sensing systems can estimate human postures. So the baseline model fails to estimate the postures of unseen activities, resulting in significant errors against all the metrics. But when the same model is enhanced by RF-Gen with no additional data collection, the posture error is reduced by 60 to 90%, and you can see all the metrics of error are reduced. Similarly, we have examined the ability of the baseline system to recognize basic poses within complex environments. However, the baseline model performance degrades when objects are near the human subject, like tables, chairs, or sofas or anything, causing significant multipath noise. And by contrast, when it's supplemented with RF-Gen, it continued to demonstrate high efficiency. For the model with unseen users, we generate data for 20 different body shapes and genders performing identical actions as a supplement, and errors related to body shape like S and T are decreased by more than 50%. Millimeter wave based gesture recognition systems often struggle with generalization when hand gestures are presented at varying orientations, which cripples their usability in practice. And then the generation set primarily covers single hand actions with 6 types of movements in total. And we choose 0, 30, 60, and 90 degrees as orientation measures. And the prompt for the data synthesis is P5 as on the right. The baseline system struggles in identifying the hand gestures, with accuracy dropping to 61% at 60 degrees and 20% at 90 degrees. But when it's supplemented with RF-Gen, there's still a high recognition accuracy of above 90% across all orientations. The authors trained gesture recognition system using the RF-Gen generated data and evaluated on real-world hand gestures tests collected from the radar device. P6 and P7 are new gestures, and the prompts for these are in the table. RF-Gen recognized these gestures with accuracies of 85.3 and 93.9%. In this figure, we can see A through E, the different human postures that they used in the previous case study, and F showing the hand gesture study. And G is just a car, which just shows the RF-Gen simulator is capable of different types of scene input. As conclusion, to reiterate, RF-Gen is a cross-modal generative framework that synthesizes and expands millimeter wave sensing data. And what does it do well? And thinking back, this was a really interesting solution. So it's a novel framework. It's new in that it combines physics-based simulations with generative diffusion models. The paper also covers detailed case studies with extensive metrics on human posture estimation and hand gesture recognition. The quantitative metrics and comparisons with real-world data underscores the validity of the results. And the paper also effectively tackles the challenge of data scarcity and the need for extensive data collection by generating synthetic data sets. Of course, there's always trade-offs to achieving the results. So the intensive computational requirements for running generative diffusion models and the physics-based simulations are definitely a weakness, and this could limit the feasibility of deploying where there's resource constraints or real-time applications without hardware investments. Next, the solution is not really tested in highly dynamic environments, especially with multiple moving objects. There probably needs to be another test for the research that has moving scenes. The paper could also benefit from a deeper analysis of potential biases in the data, particularly with the diversity of human subjects and the environments. And the last one is that RF-Gen shows promise in the case studies, but it's not clear how it can scale to other millimeter wave sensing applications. And probably detailed guidelines or additional studies could help address these concerns. And that concludes my presentation. I have references here. Thank you.
Very good. Thank you very much. Any questions from the audience?
I have the question.
Sure.
Okay, so very nice presentation. But based on the presentation and when I read the papers, I have two questions. So for my first question is, how does the RF-Gen can solve the problem of the simulated material and between the simulated material and the real material, like in the internal structures and also the accuracy of the model?
Yeah. Yeah, that is definitely an issue of having different material properties. So I think it does well when it's using both the physical simulation and the generative diffusion models together. So the physical simulations especially are able to kind of simulate diverse materials and structures through physical laws. And then the generative models capture the nuances of those effects that are not modeled in the simulation. So they still have material information there. And then the cross-modal synthesis also has iterative refinement from real-world data.
Okay, got it. Thank you. And I also have another question is that, so I want to know what's your idea about the implements of the RF genius for the millimeter wave sensors for that application, like in like the data privacy and also the scalability of this?
Yeah, I think RF Gen definitely has less reliance on collecting data since it's able to synthesize a lot of its own, and that takes care of a lot of probably potential privacy concerns because there's less capturing of sensitive information. They can just synthesize more based on the data set that it already has.
Yeah.
And
Okay.
in terms of scaling it, probably really depends on how much computational resources are available because the diffusion models need lots of resources to generate like really good solutions. So in that way, when you're scaling up, there's also the potential of generating that inaccurate data because no model is perfect, of course. And if the models are not trained well or the simulation parameters don't represent real scenarios, then some inaccurate data will come.
Okay. Got it. Thank you so much.
Thanks.
Yeah, I have some questions as well. Great presentation, by the way. So my first question is, how do you think this system's capability for sensing could change the way that this sensing tech is used overall?
Oh, yeah, that's a good question. Well, I definitely think something I really liked about this proposal was that we don't have to collect as much data, like I mentioned. So I think as we develop millimeter wave sensing tech, the people that are developing can probably prototype and test way faster. So the ideal way is to fail fast. So because they don't have to collect as much data to do another iteration, they could probably put out more prototypes faster.
Awesome, yeah. And then my second question here is, what potential future do you see in this sensing technology? Like, where could it be used?
Yep. So something that I was interested in about the paper was its potential to work with autonomous vehicles. And right now I'm working at GM and it's like a huge research thrust at the company. And I picture a lot of that with RF Gen, but it can also be applied to so many other applications in the future, like crowd monitoring for security. And given the fact that we can like synthesize new data, there's not as much privacy concerns as it would be without it. Or doing more interesting VR video games because you can like do gesture tracking. That's something that I would probably want to do.
Awesome, yeah. Thanks for those answers.
Thanks.
Any other questions from the audience? Okay, if there's no more questions, so let's thank the speaker. Very good, thank you very much.